Hey, Brennan, feel free to share your screen.
Good evening. My name is Brennan Marks. That was a long bio. Thank you very much, Lindsay. I learned something about myself. No, I appreciate you giving me the opportunity here to present tonight. And as it is a topic that is pretty close to us, and it's what we do on a daily basis. So, protecting Canandaigua Lake and this with sustainable wastewater solutions for future generations. I can get my screen to advance here. All right, so I won't go through all that again, but I will kind of touch a little bit about my past. I did grow up in a little town called Potter. Don't admit that to a lot of people, but we grew up working on Canandaigua Lake. Spent a lot of time on the lake. Spent a lot of time in Vine Valley, installing septic systems. Also doing a lot with water intakes. So it was a really good job for high school and college years, but it brought me to where I am today. I kind of led on from the contracting and construction and went to school to better my career. So tonight we'll talk about septic systems, the different components. We'll talk about a little the different types of systems, soil testing, and how you come up with a design of a septic system, and then also talk on about some topics that are pretty close to the lake as far as phosphorus goes, and how the septic systems are contributing to the phosphorus, and then also talk about some things to consider current landscape of where we're at and what we may be able to do to better the situation. Um, so what is a septic system, right? So it's us engineers like to refer to it as a on-site wastewater treatment system. But simply, it's just a wastewater treatment system installed on site that properly treats and disposes of sanitary waste. It's just got a simple definition, but it's can be the systems are pretty elaborate. So some of the components of a septic system is your septic tank. You know, you come out of the house, your soil pipe, it goes right into a septic tank. It's usually a concrete or sometimes plastic tank that has an inlet and outlet. It's got what they call baffles on it, which forces the wastewater down. But basically, what that is that it's where most of the, let's say 80% of the organic material is removed from the wastewater by just settling. Basically, it falls to the bottom and it falls into a sludge, right? This here is a picture of the inside of a septic tank, in case you're interested, and that's the sludge down at the bottom. That sludge is your heavier particles that fall, your cellulose, your fibers, and that sludge continues to digest and break down in the bottom of the septic tank, so it doesn't just fill right up. It actually decomposes into gray water. There's many of the newer septic systems have an effluent filter on the outlet. Basically, uh, it's like a screen that limits the amount of solids or bigger particles that go on to the leach field. But before we get to the leach field, we have a distribution box, which right here, you almost see it, usually made of concrete, sometimes plastic, but they basically just distribute the effluent coming out of the septic tank to equally to all the leach lines. And the leach lines, sometimes called lateral, are stone and pipe, or sometimes they call chambers or infiltrators. There's a newer technology. But basically, where the effluent, the dirty water, the gray water, sometimes referred to, basically goes through a soil-based treatment process where it builds up an organic matter on the bottom of the trench, and it distributes across the bottom of the trench, and then that microbes and bacteria will digest those organics, and then it'll infiltrate down into the ground, into the different soil horizons, but also it will uh, evaporate. 30% of it will evaporate up through the soil horizons and out through the vegetation and up into the atmosphere. Um, there's sometimes we have pumps and valves and controls that we use if we have to pump it up. You know, if the elevation doesn't work for us, sometimes we have to pump it to a higher elevation where we can put in a leach line. There's different systems. We typically refer to the simplest one is a conventional system, or sometimes called an in-ground system, which is where you have a infiltrator chamber or basically a perforated pipe that's buried with stone that distributes the gray water across that leach line. Um, so that's the most common one, or that's the one we try to put in most places, should I say. Then we get into a little bit of a advanced model, which is a shallow modified, where you actually have to bring in about 12 inches of sand or other type of soil fill that's good fill to raise it up. Usually we're raising these systems up to get them away from the water table or the groundwater aquifer or above the bedrock or even above a heavy clay layer. So sometimes we have to bring in some soil. There's a deep trench, which is not very common, which is where you have sand below a clay layer, where you dig through the clay layer and basically get the gray water to perk into that sand layer. This is not very common. There's some other systems that they're called geotextile sand filters. They're Elgin, Presby. There's some of you guys that may have heard those names, um, where they have a different technology that they use a geotextile fabric that surrounds the pipe, basically holds the organic material in that geotextile and allows for a media for that digestion to take place. Bed systems, again, not very common here because you need a higher perk rate, which we don't usually see a lot of 30-minute perk rates, I should say. It's not really practical for this area. Then there's the seepage pits, which are really not practical. They're usually 5, 6 feet in depth, but around here, if you get that deep, usually you're keyed into the water table. The seepage pits were a big thing of the past because as soon as you keyed into that water table, you put water into the pit and it soaks right into the water table and goes away. But unfortunately, they don't provide much treatment. So some of the questions, a lot of things we deal with is the cost of the system. So what we can say is system costs now for like your standard in-ground stone and pipe system, they're around $15,000, sometimes a little more, sometimes a little less. And you get into these shallow modifieds or more of an advanced like geotextile filter, you get into like could be up to a $30,000 number. That's the prices we're seeing. I figured I'd include some cost data here because that's our biggest goal is to minimize the cost, but increase the effectiveness. So then the next, you kind of go up to the next tier is an alternative system where we have to bring in proprietary products like Presby, where we're using Presby beds and some peat modules, some very expensive stuff. But first, we usually start with a raised system, which is where you're adding 3 to 4 feet of sand to the ground surface, and then you put your septic system in that. We do alternative systems where we don't have much soil. We refer to soil as like the depth of the soil above your limiting conditioning, and your limiting condition is your groundwater or your heavy clays, your bedrock. So if you don't have uh, 2 to 4 feet above those limiting conditions, then you kind of have to go to a alternative system, which um, they are more advanced, a lot more material, and a lot more money. The So mound systems are another type of raised system with a pressure distribution. Basically, you're pumping pipe into or pumping out gray water into a smaller pipe and pushing it out through a bunch of smaller orifices like a drip system. Um, the ETUs are enhanced treatment units. Are very common around the lake. Actually, it's because they're required around the lake, especially near shore, like or near within 200 feet of the lake. We're required to do what they call an NSF 245 system, which these NSF numbers, the National Science Foundation numbers, is kind of is a benchmark that we use when we specify equipment and types of systems. So NSF 40 is like basic. You get most nutrient removal. You're getting a clear odorless liquid that comes out of it. NSF 245, you're getting nitrogen reduction, nitrogen and other nutrient reduction to a level where you could just about discharge it directly into a stream if that was the case. And then you've got a NSF 350, which is actually a recirculation or a reuse standard where you could take the water and put it back into your house or put it into your irrigation system or reuse it for a non-potable source, of course. So we do a lot with these. We do a lot of Presby systems around the lake. Up here on the upper right is a tiered system in Middlesex where that's a 7 or 8 feet tall retaining wall on the bottom side, and the slope is very steep. You can barely walk on it. The lower one here is a peat system. It's on East Lake Road. That's actually my father there standing there. But we got 3 peat modules in a bed just up off the lake. And this is that Presby system, the Presby chambers that we've mentioned. It's a geotextile wrapped pipe. It's a corrugated 12-inch pipe, but it's got all this geotextile layers around it, which hold the bugs or the microbes in it, and allows the effluent to filter down through that and get treatment along the way. So it comes out of that actually as a almost clear, odorless liquid by the time it comes out of this Presby pipe. But so we start our design with a soil perk test, right? It's not rocket science here. We dig a 2-foot deep hole, about 8 inches in diameter. Usually use post hole diggers if anyone's ever installed a fence before. You put a stick in it or a lath with a nail and the 2 nails in it, 5 and 6 inches up off the bottom. You basically just time how fast it goes down between the 2 nails, and you do that 3 or 4 times, and then you get a perk rate. Your perk rate needs to be less than 60 inches in order to do a conventional system, or 60 minutes per inch, sorry, in order to do a conventional in-ground system. We use that basically as one of our design standards, our test methods to design. Sometimes we'll do it at shallower depths depending on how much soil is on the site. The next one is probably one of the most important ones, is a deep hole test, where we just dig a hole with an excavator or backhoe. It's got to be about 4 feet, sometimes 6 feet deep. We're just looking for evidence of high groundwater. We're looking for soil changes. So, for instance, in this picture, you see it turns to a white. So that's all topsoil below, but as soon as it hits the white or lighter colored or gray or even rust color soil, or even sometimes pure white soil, is evidence that you have a high water table. What happens is it's an oxidation reaction. When the water comes up, it oxidizes the minerals in the soil, whether it rusts them into a rust color, or it deposits calcium into a fine white chalk, or just bleaches out the soil. And then, well, as it resides, that oxidation is evident that we have a high groundwater elevation. Then we have to stay, 2 feet above that. So one of the most important things, as you can see in this hole here, this is ground. We got water right at the bottom of it, but other than that, we're also telling that this smeared the whole sidewall going down. So that's some really, really thick, heavy clay, and that I guarantee you was a raised bed system there. But we're looking for that modeling layer, the oxidation layer. That's basically tells us what our depth of soil is. Sometimes it's very evident. Sometimes it's very not. It's very hard to tell actually. So a little bit of art there, but yeah, we have to stay 2 feet above that modeling layer, and that's kind of dictates what kind of system we can put in. So good practices for putting a septic system in, or good practices for having a septic system in your house. The main keys are 100 feet away from the well. Obviously, we don't want to recycle our wastewater, right? And we want to be 100 feet away from a water course, whether that's a stream or a lake. We try to stay as far as we possibly can away from any like drainage swale or drainage ditch or other surface water and then also 100 feet away from wetlands. Other general things we're trying to accomplish when we site a septic system is on the flattest possible piece of ground you have. With the deep hole test, we're looking for the greatest depth of soil right above our bedrock or above our water table. We want to minimize pumping, so we want to get gravity right out of the house to the septic system. It's not always possible. Sometimes we'll have to put a pump in and lift it up to a different area of the ground of this property. We want good vegetation. We want to have we don't want to have trees that we obviously have to take down, but we don't want to have trees, large woody trees over top of the system because they'll fill up the lines with roots and they'll plug them solid. But 25, 30 feet around the system, a good tree hedgerow or woody mass is actually really good for taking up some of the nutrients that do leach out around the system. Um, we want to maintain, we need a good lawn cover. We obviously don't want to put this in a shale or something that won't grow grass. Um, and then also when we're looking at new sites or even old sites is we don't want to put the septic system in a hole where the surface water is going to kind of collect in there and flood out the system every time it rains. So we're usually looking to divert some of that surface water around the system or drain it away from the system. And then other big things are like your roof gutters and your downspouts. You got to know where your septic system is and keep those directed away from your leach field. And I see it all the time with sump pumps. They pump it right out on top of the leach lines, and it's like if you got good soils, yeah, it's probably going to be all right. But if you got tough or marginal soils, you're probably going to wear that system out in half the time. So um, we're also kind of conscious of when we, especially new construction, and some of the groundwater changes. When you build a house and put it in a basement, you're going to drain a lot of the groundwater out. But also, if you're putting in a driveway or other types of practices that may compact the soil horizons, you may actually maybe creating an underground dam and damming up the groundwater so that it actually pools where your septic system is. So we're conscious of that. So that brings you to our thing is a little bit of a marketing here is this is why you need a septic system. So you think about all this stuff, or this is why you need a site plan. So you think about all this stuff when you're designing your septic system. Um, but we do a lot of site plans for new construction and also septic systems to make sure that we're taking into account our separations, our soils, making sure we know where the property lines are. Don't like to put leach fields over property lines. It's happened before. Making sure we're conscious of the grading and drainage, and then also, especially in the watershed, is compliance, right? We've got to get a permit for it. So we have to have a plan to show that we're in compliance with the codes. And then also, as a big thing for homeowners is if you have a plan, you can take it out to a contractor and get a solid price on it. And there's no guessing, right? You can get two or three and then have, a good procurement policy that you're not worried about one missing something or coming in with half the project. Some of our design fees, they range from around $1,500 to $6,000 for these site plans. The design, like 1,500 is like kind of our going rate for a replacement septic. And then obviously you get very advanced into these septic designs and it can go quite a bit higher. So um, next, so I wanted to bring us into like how does this relate to some of the harmful algae blooms and stuff that we've had around the lakes? And uh, we know I, we see it too, and like how can we help with these septics? I know they're only a really small portion of the phosphorus loading on the lake. I think it was less than 10%. Um, I don't have that figure exactly, but the phosphorus is in many forms, but mostly it's uh, called orthophosphate in wastewater. It comes out of the pipe from your house to your septic tank. It comes out with 10 milligrams per liter of phosphorus. That's kind of a standard level. And actually, the funny thing is, I did a little research into this, and over 30% of that is actually just urine. So detergents used to be a really strong generator of phosphorus, but they've actually really toned that back so there's minimal phosphorus in detergents anymore. Household detergents, should I say. Um, Phosphorus is actually kind of hard to digest or degrade. It's mostly minimized with ion exchange or oxidation when it reacts with aluminum or iron or even calcium. Um, it's a negative charged ion. It bonds to iron and a participant that becomes a heavy participate and it falls out of solution. It'll bond with some of the chemicals that make up of limestone and form a precipitate, but it's a lot. That's a harder process, which is but another thing is it's removed through soil adsorption, not absorption, adsorption, where it's binding to these soil particles, and it's remains in the soil horizon that's 2 feet below the leach line, and it further oxidizes and biologically decomposes in the soil profiles. I saw there was a question. Oh, sorry. Um, vegetation uptake is a big part of phosphorus removal too. It's absorbed into the plants and vegetation and used for growth. A standard septic system will remove 57 to 75% of the phosphorus from the wastewater, which is actually pretty good. But a failing or a septic system that's directly influences groundwater or is in the groundwater table, there's very little removal, and it actually, transport out to the water course, the nearest water course. Here's a picture of a distribution box, but I brought this. I put this on here because it's mostly clear water in there. That's just groundwater. It's basically completely flooded with groundwater, and it works. It takes all the water you can give to it, but it's because it's going straight into the groundwater aquifer, and then also the groundwater is coming back into the D box. That's why it's nice and clear. This is a picture from Wastewater Lake where they have pretty big algae bloom there. So a funny little or a little fact I picked up from EPA was phosphorus may be the limiting nutrients when it comes to these harmful algae blooms, but actually it's the algae blooms are so rich in phosphorus that nitrates, the nitrogen, fuels it and makes them more widespread, and also enhances, lengthens their lifespan, how long they stick around for. So not only are we got to be considered about phosphorus, we should also be considered about our nitrates and our nitrogen. Um, so things to consider. Um, we pay very close attention to the septic systems around the lake. We use the 200-foot rule, 200 feet from the shoreline. We're really focused on those. We consider uh, more of an enhanced nutrient removal process where we're removing more nitrogen. That is a standard now, but also removing phosphorus with different practices that could be implemented to help reduce the nutrient loads. Things that we don't really pay much attention to as far as the watershed program goes is some of the septic systems around the major tributaries. The Reservoir Creek and Sucker Brook and um, some of the other ones here that down in Vine Valley, there's some septic systems that are very close to the tributary system, and the most likely is a lot of them are right in the water table. Those are we should be very pay closer attention to those. And then also there's rehabilitation programs. I'll get into that. All right, so some facts that I've gotten. I talked to Tyler Oley, our watershed inspector, a little bit. He says there's about 515 septic systems near the Canandaigua Lake shore, about within 200 feet. He says 321 of them have enhanced treatment systems. These are likely newer systems. They're probably installed correctly. They're probably doing that 75% removal of phosphorus. 86 are holding tanks. If the tanks are in good condition, those should not be a problem because they're being pumped out. 39 of them are conventional systems, and then there's 69 of them that are not in compliance with the inspection program, or they're older than 30 years. So I usually use that 30-year lifespan on a septic system. Anything after that, you're kind of on borrowed time. So those 39 conventional systems could be enhanced to like a nitrogen removal system, and they could be retrofitted. And I threw some general costs in here. If you put $15,000 into each one of those 39, you could have $600,000 worth of upgrades. It would help reduce some of those nutrients. And then at those 69 systems that are older than 30 years and not in compliance, which are likely going to be, most of them are going to be your problem systems. I just use a general rule here. We see higher costs like $35,000 for a septic system on the lake is usually a challenge. Could possibly cost $2.4 million to replace all those. Those, like I said, those problem systems are probably your most likely your problems, like with as far as the phosphorus loading. Then there's new technology that's coming out, which I'll talk about in another slide, is dual nutrient removal systems, where they remove the nitrogen and phosphorus. There's, like I said, it's very emerging technology, and it's not well advanced yet, but and I can't really associate a cost to it, but there is solutions out there for those coming. So current landscape, there's septic systems near the, like I mentioned, near major tributaries. There's about 1,200 systems around the major tributaries. Um, there's limited data, limited inspection protocol. There's the watershed inspector does not have to inspect any of those. You know, if the watershed uh, inspection program was expanded to 200 feet from all the major tributaries, that would definitely help reduce some of the phosphorus loading. Here in the middle is, like I mentioned, those seepage pits here in the middle. This one, you can see that's just laid up concrete blocks stacked up. It's probably 5 or 6 feet deep. Well, all the water you can put into it just goes right down and goes into that shallow aquifer and basically goes right out either to the lake or to the nearest water course. Um, you know, it's kind of like a reverse dug well if you think about it. So um, this on the right here is a Presby system we put in. It's down on the lake. It's greater than 250 feet from, or 200 feet from the lake, but it's shallow. And it's another enhanced treatment process. So enhanced phosphorus and nitrogen removal. I mentioned the soil adsorption being one of the best removals of phosphorus. Uh, when you have that uh, plenty of soil beneath and around the system, that you know the nutrients or the phosphorus will stay local to the septic system. But if your system is within 200 feet of the lake, it's probably going to get to that lake or major tributary. Um, NSF 245, which is our nitrogen removal, every system within 250 or 200 feet from the lake has to be a 245 now when we replace them. So you're removing the nitrogen. But some of these emerging technologies for phosphorus removal are pretty interesting. They use in municipal wastewater treatment, they use metal salts or aluminum, they call it, or ferric oxide. Basically, they put right into the wastewater. It bonds with the nutrients, and they precipitate out, and then they're taken off with the sludge. But obviously, that's not a practice we're going to do with residential wastewaters. I don't see anyone putting metal salts down the drain, so probably not practical for on-site systems. Um, there's a filtration media, which is an iron-based media that's over here like this Noeco. They call it a phosphor fade. Basically, the water's filtered up through an iron or a media that's got a oxidizing agent in it, and then it pulls those phosphorus nutrients out. Problem with that is this media is going to have to be changed at some point, which is going to be a challenge. But you're going to remove the phosphorus. Peat filtration is another common way to remove phosphorus. Like I showed you, those peat filters or peat beds, peat modules. Um, that's a common practice. And then, but also you have to change the media on that. There's a new one coming out of a Canada company. It's basically uses electrolysis, similar to a battery, but kind of in reverse, where they put a positive and negative charge to iron plates, and basically the iron oxidizes off the plates and bonds to the phosphorus, and then creates that heavy particle and precipitates to the bottom of the tank. That one is newly it's a new process, a new technology, and I'm excited to see how that turns out. So the septic rehabilitation program, I was in ESF. I was a part of a CAT skill program where there was a lot of studies and testing going on the effluence of septic systems and the different types. And one of the things that came out of that program was The Catskill Watershed Corporation basically came up with a complete replacement costs, up to $30,000 will completely replace the septic system in the watershed. I know that the county has their $10,000 grant for systems that are directly next to, or they're near priority water bodies. Um, the, that 10,000 is doesn't really cover much if you look at the grand scheme of these things, especially around the lake. But $30,000 would. And if you could expand it to the whole watershed, not just around the lakes, that would definitely be a um, big plus. Just some fun little facts here about the Catskill Watershed Program. So they replaced about 7,000 septic systems as of 23. But the biggest thing is they're funded by New York City. That's where New York City gets their drinking water from, and they've got huge money from the city. But like you mentioned earlier, is Canandaigua Lake is a water source for about 70,000 people. So that maybe they can help share in the cost of a rehabilitation program. But other things that you can look at that I recommend is just covering the cost of pumping and inspection. That it would uh, help our inspectors get these problem systems uncovered and on the radar. Um, so the grant funding is, I'm sure, is a challenge, and there is some grant funding from the Environmental Facilities Corp, but also there's funding out there for water treatment and water users. So from the health department, maybe consider a source of funds for these rehabilitation. Um, so with that, I guess I that's all I have to say tonight, and I'd be glad to answer some questions. Uh, I did see one come up from Michael Seneger, um, the effective farming around the lake, and I think that conversation has been a big conversation for a while, and I know that the watershed has done a lot of projects to capture and runoff from farm fields and cultivated land to help reduce some of that nutrient loading. But if anyone's got any questions, I'd feel free to answer them. Take them. Brian, Brian Heminger is one of our surveyors. Yes, Brian, we do have a fantastic survey department. Thank you.
Any other questions, folks, for Brennan? You must have answered everything so thoroughly for us, Brennan, that
It's either that. I mean, 7 o'clock at Wastewater is a tough conversation. I know.
all right. Another, oh, we got one popped in here. It says from Catherine Gardner, we have a system that was installed in 1989. It is a raised bed. How is the system tested to see if if it's doing an effective job?
That's a very good question. Well, the general test is can you see it? Can you see wastewater? Actually, you know what? The vegetation is really the telltale sign. If the grass is green and you don't see water breaking out on the surface, and there's no dead spots or odor, it's probably still doing its job. It's probably doing what it's meant to do. The the funny thing about raised bed systems is that if the water bleeds out of the toe of the system where the sand meets the original ground surface, it's considered treated water. It's considered fine for surface discharge. Now, if the system is not put in right or has found a weak point in the sand, it could be a source of pollution. I saw that Wade had a question there, so.
Oh, yeah.
Comment on the requirements regarding the size and bedrooms. That's a very good question. The watershed uses 150 gallons per bedroom per day, which is per person, around the lakes, and then if near the lake, should I say, and then as you go up from there, It goes down to 150, 130 gallons per person per day. We find that, that is right in line with the typical water consumption per bedroom, because a lot of times we're doing designs with multifamily housing or hotels and whatnot. So we study the water usage previous, and we do find that, a person uses about 100 gallons per day. But the model of designing it per bedrooms only works if there's one person per bedroom. And we know that some of these houses are getting overloaded and or they're adding bedrooms after the house is constructed and not upsizing the septic. And that is a common reason for failure that we see around the lake.
And it looks like you had like a follow-up question as well from Wade. And can short-term rentals, VRBO, Airbnb overwhelm systems with excessive use?
Absolutely. They can, I mean, as soon as you put double the load, right? Say an average household, which is 450 gallons per day for 3 bedrooms, 3 persons. So, but if you put 6 people in there, you're theoretically putting 900 gallons out the pipe. The septic tank isn't going to settle out solids fast enough. It's going to make its way to the leach field. You're going to flood that leach field with solids and organics that it can't decompose, and the lifespan of that would be less than half of what it was supposed to be. There's a question from Dee Dee.
Oh, yeah.
What if you have less? What if you have less than 100 feet from the lake and it's grandfathered in? What are your options? That is tough. Usually, when I look at a site that has less than 100 feet from the lake, we look at options that to put a system on a neighboring property with an easement. And that's the thing. You don't have to own the property. You can purchase or gift an easement to someone so that they can put their septic system that's away from the lake, far enough away from the lake. If we can't do that, then we belts and suspenders the treatment process where you've got like an aerobic digester that's rated for nitrogen removal, and then you put it to a leach bed that is rated for enhanced treatment. Treatment also, and that'll get you a septic system. Obviously, the holding tank question comes in there, whether you should be on a holding tank or if you're allowed to have a system. So that's a really hard conversation, but that is why the grandfathered in is the reason why they have leniencies on the code for replacement systems, right? You have a septic system now, and you theoretically could keep it, which you shouldn't, but you should be able to replace it. So we get into those systems quite a bit, and we basically just treat it with belts and suspenders and just providing as much treatment as we can before the waters exits the system.
Oh, there's another one from Peter. Hey, Brennan, are there any sewer feasibility studies that are looking at taking portions of the watershed off of septic and diverting wastewater to the treatment plants? I know New York City reimburses construction costs for on-site wastewater treatment systems that were recently installed in newly sewered areas.
It's a good one. So now we're getting into a little bit of a political discussion with the sewers around the lake. Yeah, I think there should be more sewers, especially for some of the tougher areas of the lake that can't have septic systems or don't have enough room or soils to have septic systems. The problem with sewers is you're just inviting more development. So it's a little bit of a double-edged sword. So, and then you're going to have people that want smaller lots and more housing. So, I still think the decentralized approach for like having rural septic system versus a municipal treatment plant is a better way to treat wastewater is having many little systems versus one big one. And then I think the cost of putting in septic systems is going to be less than the cost of adding sewer to the problem lake also. So Sue has a question. In June, we received a letter from Ontario County Public Works saying our property was identified by the New York State as being located in a priority geographic area. Is this grant program to replace septic still going? How do we know if we need to replace? That is a good question also. Sue, I would start with an inspection. There's a lot of people that we can inspect or any lot of, they call it OTN, on-site train network. Anyone could inspect it. Basically and most of them are your septic pumpers that are OTN also. They'll pump the tank and make sure that it's working right. Then if it is not working right, obviously right there is maybe we should start thinking about replacing it. And then that's where that grant really comes into play. But if it's too close to the lake and it's still functioning, I think you still qualify for that grant. And if there's a lot of ways to find that it is not compliant with regulations, but also it is compromising the priority water body, so that you may still be able to qualify. It doesn't necessarily have to be a failed system in order to qualify for that grant. Okay. And then Michael Siniger, are holding tanks an option? Absolutely. There's a lot of sites where you come to it and say, this just needs a holding tank. There's no way that we're going to get a system here. And the way the health department reads in their regulation, it says that you have to prove that you cannot put a septic system on the property in order to design it as a holding tank. So not to say that we have to go through full site designs or site plans to prove that a septic system can't fit on the site. It's basically, if you don't have enough area or if the area is too close to the lake, absolutely. Holding tanks are very expensive, not to install, but to pump out. If you're thinking $300 a tipping fee every time you pump it, and if you're using a 3-bedroom house is using 450 gallons per day, you get 1,000 or 1,500 gallon holding tank. Theoretically, it's supposed to be full in a little over 3 days, but obviously people in holding tanks are very conscious of their water usage, and which is actually a good thing in conservation also. So if it's a seasonal cottage and that's all you can do is a holding tank and you can be very conscious of water usage, I think it's a very good solution. So
Any other questions for Brennan? And obviously his contact information is here on the screen. So if you have any follow-up questions for him.
yeah, feel free to shoot me an email, call, stop in. We'd be glad to answer questions about septics. My wife jokes with me is the king of poop. So
I think you had that one coming with
yes, I think so. Thank you, Sue. I appreciate that.
Great. Well, if we don't have any further questions, again, just reach out to Brennan, or if you have any other questions for us, we're going to make this recording available on our website, and we may share it through our e-blast coming up as well. So we thank you all so very much for joining us tonight, and for Brennan for putting this great presentation together. We're lucky to have people doing work like this that you're doing, because I certainly wouldn't have any clue where to even start, but it's a fascinating process. It's a necessary process. So we're very thankful for you and all the inspectors out there. So thank you so much, everyone. I hope you have a wonderful rest of your evening. And as I said earlier, stay tuned for some other presentations we have coming up. Like I said, Brennan's colleague will be doing a presentation sometime in March, which will be through Zoom as well. So other than that, have a wonderful evening, stay warm, and enjoy the rest of your night and your week.
Thank you.
Thanks again, Brennan.